Today we've got a really nice number theory problem that comes from our favorite problem suggester. So this person used to be known as the integral suggester, but now they suggest all sorts of nice problems. This one was also found in a 1956 issue of the American Mathematical Monthly. So let's see what our goal is. We'd like to find the 2,319th digit of 1,000 factorial. And we're going to use a couple of well-known tools. The first is this formula that determines the number of times a prime p divides n factorial. And that's given by the floor of n over p plus the floor of n over p squared plus the floor of n over p cubed plus so on and so forth. And we generally write this as an infinite sum, although it truncates at the point where the power of the prime is larger than n, and thus the floor becomes 0. And then we're also going to use something called Stirling's formula, which is a large value approximation of n factorial, and it's a really good approximation. In fact, I've got a video that I've recorded for the channel about Stirling's formula where we derive it that should be coming up soon, or perhaps it's already been posted. That says that n factorial is asymptotic to the square root of 2 pi n times n over e raised to the n power. Okay. So now let's get to using this first tool to determine how many times 5 divides into 1,000 factorial and how many times 2 divides into 1,000 factorial. That's because our goal is to determine the number of trailing zeros in 1,000 factorial. Okay, so let's first look at the number of times that 5 divides into 1,000 factorial. And we're gonna, like I said, use this formula over here. So we'll have 1,000 divided by 5. Well, I've got the floor here, but of course I don't need the floor because that's a whole number. And then we'll have plus the floor of 1,000 divided by 125, or 25, plus the floor of 1,000 divided by 125. So there that is, I got ahead of myself. And then let's see, we've got one more, and that is the floor of 1,000 divided by 625. And so let's talk a little bit about why this works. So this first number counts the number of multiples of 5 that are between 1 and 1,000. And of course, because 1,000 factorial is the product of everything between 1 and 1,000, well, that counts the number of 5s that we encounter. But notice that every time we encounter a multiple of 25, we pick up another 5. And so that's what this is counting, the number of times that we encounter a 25. And then, well, if we encounter 125, well, we're going to pick up another factor of 5. So that's what this is counting, and so on and so forth. And like I said before, this number is truncating, and in this case, it's truncating at this point. Because if we were to look at 625 times 5, which is like 3,000 and something, well, the floor of 1,000 over that would be 0. Okay, so anyway, now let's write this down. So 1,000 divided by 5, well, that's pretty clearly equal to 200. We don't need the floor. Plus 1,000 divided by 25, that's pretty clearly equal to 40. We don't need the floor. 1,000 divided by 125, that's equal to 8. We don't even need the floor there either. But then 1,000 divided by 625, well, that's pretty clearly equal to 1. That's because 1,000 divided by 500 is 2, and then 1,000 divided by 1,000 is 1, and so that means 1,000 divided by 625 is between 1 and 2, making the floor 1. So that means here we have 249. So that means that, well, we can write 1,000 factorial as 5 to the power 249 times something right here, which is not a multiple of 5. Okay, great. But now let's look at the number of times 2 divides into 1,000. So we'll get that going here. 2 divides into 1,000 factorial. Well, we've got 1,000 divided by 2, the floor of that. 1,000 divided by 4 plus 1,000 divided by 8, so on and so forth. The last thing will be 1,000 divided by 512. That's because the next power of 2 is like 1,024. The floor of that would give us 0. So adding all of this up, we get 994. Well, 994 is bigger than 249. So the extra values of 2 won't really be super helpful. But needless to say, we can take 249 of these, group them with the powers of 5, and then we'll have a power of 10 that we can divide out of 1,000. So like I said, putting this all together, we have 1,000 factorial is equal to, well, it's going to be 10 to the 249 times, well, it's going to be an even non-multiple of 5. So we know it's going to be even because we've got leftover powers of 2 from this formula. We know it's a non-multiple of 5 because we used up all the multiples of 5. So that means it has the following form. So it's got all of these digits kind of at the beginning, and then it's got a single digit right here, which we know is even, and then it has a bunch of zeros, and it has exactly 249 zeros. Okay, so that's good. We've got some sort of idea for the structure of this number 1,000 factorial. Now we just need to determine, well, where does this 2,319th digit sit? And in order to do that, we're going to use Stirling's formula. Okay, so far we know that 1,000 factorial has this big chunk at the beginning, and then it has an even digit, and then it ends in 249 zeros. So that means it's a multiple of 10 to the power 249, but no other multiple of 10. It's got some multiples of 2, but no other multiples of 5. Then our next goal is to determine how many digits are there in 1,000 factorial. If we know the total number of digits, well, we'll know how many digits are in this number right here, and thus we'll know the position of this even digit. And spoiler alert, well, there's something special about this number, 2,319, with respect to this picture of 1,000 factorial. Okay, so we're going to use the following fact, which is fairly clear just based off of the definition of the logarithm, and that is the number of digits in a number capital N is equal to 1 plus the log base 10 of capital N. Okay, well, that means that the number of digits in 1,000 factorial, well, that's going to be equal to 1 plus the log base 10 of 1,000 factorial. But now we're going to replace 1,000 factorial with its approximation via Stirling's formula. And I'm going to step back a little bit and just point out that at this stage I'm following the solution from this article. But I also found some examples online where just inputting this Stirling's formula approximation into this digit rule doesn't work. So I do think this is kind of sketchy, but that being said, I think this is probably a relic from the fact that this was done in 1956 when calculating large numbers were very difficult. In fact, they make a special point to say that someone in fact calculated 1,000 factorial, meaning that this was quite a feat. But that being said, I can calculate 1,000 factorial in Mathematica in like a quarter of a second nowadays. So this is not a big feat nowadays. So anyway, we're going to use Stirling's formula as that's what's done here and that's what works here. But I will say that it is a bit sketchy. Okay, so notice that using Stirling's formula, this is 1 plus the log base 10 of, well, note we have the square root of 2,000 pi, and then we'll have 1,000 over e all to the 1,000th power. from here what we can do is use some logarithm rules a bunch of times. That's going to give us something like this. So we're going to have 1 plus 1/2 times the log base 10 of 2, and then plus 1/2 times the log base 10 of 1,000 plus 1/2 times the log base 10 of pi. So that's from deconstructing this 2,000 times pi, which clearly comes from this 2 pi n portion. And then next we're going to have plus 1,000 log base 10 of 1,000, and then minus 1,000 times the log base 10 of e. That's from this bit right here. And then at this stage, we're going to use some approximations. And here are the following approximations. So the idea is you want to look for powers of 2, powers of pi, and powers of e that are close to powers of 10. And those are going to fuel your approximations. And using that and then maybe resolving for pi, e, and 2, we'll have pi is approximately equal to the square root of 10. Well, that makes sense because pi squared seems like it should be close to 10. And then 2 is approximately equal to the 10th root of 1,000. So that makes sense because 10 or 2 to the 10 is 1,024. And then similarly, e is approximately equal to the cube root of 20. You can check that e cubed is around 20. Okay, so putting all of that in here, you'll see that you get something that is approximately equal to 2,568. And then, like I said, I feel a little bit sketchy about this, but for the purposes of this video, I didn't think it was really worth it to do like a fine-grained approximation to make sure that this was right. But in fact, this is the number of digits of 1,000 factorial. So Stirling's approximation works in this case. But then looking at this decomposition right here, if you take 2,568 and subtract 249, you'll get exactly the number you need. You'll get this 2,319. So that means that this number right here, this even digit, is the 2,319th digit. So that's good. That gives us some sort of insight into how to continue on this problem. Okay, so let's go to the next step. Okay, so far we've decomposed our number 1,000 factorial into a bunch of digits, and then this 2,319th digit sitting by itself, and then 249 zeros. And our goal was to find that blue digit right here. So put into other terms, we really want the last digit of 1,000 factorial divided by 10 to the 249, because that'll cancel all of these zeros. But put into the language of modular arithmetic, this is equivalent to finding 1,000 factorial over 10 to the 249 mod 10. Okay, so we're going to do this last couple of steps a little bit at a time. So let's first decompose 1,000 factorial over 5 to the 200. And then we'll go from there. And let's recall that that 200, well, that was equal to 1,000 over 5 based on that formula for counting the number of times that 5 divided into 1,000. So just keep that in mind. Okay. So this is going to be equal to 1 times 2 times 3 times 4, but we skip 5 because we've divided it out. So I'll just put a yellow 1 there to show that we've divided 5 by 5 to give us 1. And then we'll have 6 times 7 times 8 times 9. But then the next number would be 10, but we've divided 5 out of it, leaving a 2. And then after that, we'll have times 11 times 12 times 13 times 14. But then after that would be a 15. But again, dividing 5 out of it would leave us a 3. And now you can maybe see the structure that's happening. After that, we'll have 16 times 17 times 18 times 19. After that would be 20, but we divided 5 out of it, leaving 4, and so on and so forth. So let's see where that will end. So this will end at like 996 times 997 times 998 times 999 times, well, it's going to be 1,000, but that's divisible by 5. Divide the 5 out of it, and we'll have 200. But that's going to be in yellow. Okay, great. So what does that mean? Well, now if we take all of those yellow numbers, notice that those are building up to have 200 factorial. So we'll have 200 factorial, and then times the product of everything between 1 and 1,000 that is not a multiple of 5. So that's what we're uncovering here. And I think we can see the structure in there. Okay, so now what we'll do is play the same game on the number 200 factorial. Okay, so let's take 200 factorial, but instead of dividing by 5 to the 200, we're going to divide by 5 to the 40. And that's because 200 divided by 5 is equal to 40. So now the same kind of game is going to happen here. We're going to have 1 times 2 times 3 times 4 times 5, but we've divided that out. So we've got this yellow 1 left over. And then we'll have 6, 7, 8, 9. We'll have a 10, but we divided a 5 out, leaving us a yellow 2. And then so on and so forth. So this is going to end in 197 times 198 times 199 times, well, 200, but we've divided a 5 out of it, leaving 40, but that's in yellow. Great. So now let's see what we get from that. So that's going to leave us with, well, we've got a 40 factorial. And then after taking all of those yellow numbers out, notice we've got a product of everything between 1 and 199 that's not a multiple of 5. So let's get that on the board. Great. And now we're going to play the game again with the number 40 factorial. So let's take 40 factorial, and we're going to divide 5 to the 8 out of it. That's going to leave us with 1 times 2 times 3 times 4 times, well, 5 divided by 5, which is 1, and then times 6 times 7 times 8 times 9 times 10 divided by 5, which is 2, and so on and so forth. That's going to end in 37 times 38 times 39 times 40 divided by 5, but 40 divided by 5 is 8. So there we've got this 8 left over. But then we've got the similar structure. Notice that we have 1 times 2 all the way up to 8, so that gives us an 8 factorial. But then we've got the product of everything between 1 and 39 that's not a multiple of 5. Okay, cool. But then that leaves us with one last thing, and that one last thing is pretty quick. Notice we have an 8 factorial. We're going to divide that by 5 to the 1, leaving us with 1 times 2 times 3 times 4 times 6 times 7 times 8. We just simply leave the 5 out of it. Okay, but now let's kind of decompose this into really the useful parts. So notice that this is exactly 100 groups of things of the following form. So 1 times 2 times 3 times 4 times 6 times 7 times 8 times 9 modulo 10. Well, the first one, we see that we don't really have to reduce mod 10. The second one, if we reduce all of these mod 10, we get exactly what we had here, but we have 100 groups of that. But that's a fairly easy calculation to do that product and reduce mod 10. And what you'll see is we get this. This is 6 mod 10. Okay, nice. But then we're going to have the same kind of game right here, but we don't have 100 groups in this case. How many groups do we have now? We have 20 groups. So this is going to be, like I said, 20 groups of, well, 1 times 2 times 3 times 4 times 6, 7, 8, 9 mod 10, which we determined was 6 mod 10 before. And then, well, what do we have down here? Well, the same kind of game, but now it's 4 groups. So this is going to be 4 groups of this thing. And then finally, we've got one group of things like this. But we might as well reduce this mod 10, and what you'll see is that 1 times 2 times 3 times 4, 6, 7, 8 is congruent to 4 modulo 10. So now let's maybe smush all of these things together and see where we are. Okay, so putting this all together, we have our number 1000 factorial over 5 to the 249. Well, that's congruent to this big product, which we argued was 6 to the 124 times 4 mod 10. But then you can calculate 6 to the 124 pretty easily. Notice that 6 squared is equal to 36. So that means that any power of 6 is 6 mod 10. But then 6 times 4 is 24. That gives us 4 mod 10 very, very quickly. Okay, well, that means that 4 is the last digit of this number. But this isn't the number that we want the last digit of. We want the last digit of 1000 factorial over 10 to that power. Okay, so let's do that. So let's suppose that 1000 factorial over 10 to the 249 is congruent to a modulo 10. Okay, but then we can multiply both sides by 2 to the 249, and we'll see that 2 to the power 249 times a is congruent to 1000 factorial over 5 to the 249. Again, just cross multiplying that up, but that was congruent to 4. So this is congruent to 4 modulo 10. Okay, nice. But now we've got just this congruence right here to solve. Now that's perhaps a little bit tricky because 2 and 4 are not relatively prime to 10. But what if we instead look mod 5? Well, we'll have 2 to the 249 times a is congruent to 4 modulo 5. But let's note that 2 to the 4 power is 16, which is 1 mod 5. But then 248 is a multiple of 4. So that means that 2 to the 248 is also congruent to 1 modulo 5. But if you multiply just another copy of 2 on there, this congruence turns into 2 times a is congruent to 4 modulo 5. And now we just have to multiply by the inverse of 2 mod 5, which is 3. That's because 2 times 3 is 6, and 6 is 1 mod 5. So multiplying both sides by 3, we'll get a is congruent to, well, 3 times 4 is 12, but 12 is 2 mod 5. So here we have 12 is 2 mod 5. But now branching this back into things mod 10, that means that a is either 2 mod 10 or it is 7 mod 10. Because those are the only things mod 10 that are 2 mod 5. But let's recall that we knew that this was an even number. I haven't got it written on the board right now, but we had that before. But if a is 7 mod 10, it is not even, which means we have a is 2 mod 10. In other words, this digit right here that we had as our goal is equal to 2. So if you're still around, thanks for sticking around. And if you haven't subscribed yet, maybe consider subscribing. It would really help us out. And make sure to keep an eye out for the Stirling's formula video. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.